Fraser, and I just solved the California water crisis. I'm an amateur inventor, a garage inventor if you will. 2 years ago, I heard about the drought that much of Central and Coastal America was experiencing, including some scary rumors that Lake Mead was drying out. So I flew down to the Hoover Dam to see if the issue was overblown or not. I was shocked to see the water level in Lake Mead had dropped more than 60 feet. So the water shortages were real. Once I got home, I began investing all my spare time into studying the American drought. It quickly became apparent that California was one of the hardest hit states. So that fact, combined with the realization that much of America's food comes from California, it made sense to fix California's water challenges first. And that's what I did. Two and a half years later, I had solved the California water crisis, and that's what we're going to be talking about today. As the Lieutenant Governor recently pointed out on television, the issue isn't a water storage problem. In fact, I've read that California has over 1,400 named dams and over 1,300 named reservoirs. So water storage is not the problem. The lack of fresh, clean drinking water is the issue at hand, and that's the issue I've solved. My invention will allow California to take advantage of untapped water resources and newly available sources of water. First, I'm going to go over my solution to California's water crisis in a very simplistic manner, just so you can understand the fundamentals of the concept. Next, I'm going to zoom down and focus on each step of the process. After that, I'll begin going into more finely detailed technical explanations, including the beneficial byproducts of my invention, like the phenomenal amount of green energy electricity it would generate as a byproduct of the system pumping water to those in need. And finally, I will go over some of the potential environmental challenges such a system could create, along with any mitigating factors. I've named my invention the Oceanic Freshwater Containment and Transport System. California literally has hundreds and hundreds of inaccessible rivers dotting its coastline that even in times of great drought pour massive quantities of valuable fresh clean river water into the ocean 24 hours a day, 7 days a week, 365 days a year. The challenge lies in accessing that water from those previously inaccessible rivers, gathering it and transporting it to California's dry cities and reservoirs. You see, when you try to move fresh water over land, it's very expensive, complicated, and frankly, often almost impossible, considering all the different stakeholders involved, like landowners, regulatory commissions, and multiple levels of governmental bureaucracy at the state, county, and municipal levels. My solution is to leverage the actual ocean itself as a place underneath the surface of which we connect the inaccessible rivers via an underwater piping system. That system would transport the fresh river water a few hundred yards offshore to an offshore underwater storage and piping system running for hundreds of miles up and down the coast of California, delivering previously inaccessible fresh, clean river water to any California coastline locations parallel to the system. This offshore underwater piping system is essentially an underwater reservoir for freshwater storage and transport. For brevity's sake, from now on I will simply call it the underwater reservoir. So, the underwater reservoir would be installed underneath the ocean's surface a few hundred yards off the California coastline out at sea. The underwater reservoir would be high enough off the ocean bottom to avoid damage from the ocean floor and rough seas, and also be far enough under the ocean surface to avoid boat hulls and propellers. The underwater reservoir would contain billions of gallons of fresh water supplied by the plethora of rivers along your coastline, depending on the length and diameter of the system and the number of rivers supplying it with fresh, clean water. In its entirety, the oceanic freshwater containment and transport system would act similarly to the arteries and veins in the circulatory system of a human body. Only here, we would be circulating fresh water instead of blood. The arteries and veins would be input feeder pipes and output feeder pipes, respectively. The input feeder pipes bring fresh, clean river water inside the underwater reservoir from the previously inaccessible rivers dotting California's coastline, and output delivery pipes would pump that fresh water out at strategic locations anywhere along California's coastline running parallel to the system, including cities and inland reservoirs. That's the most simplistic way of putting it, and I can also just quickly do a drawing on the board just to show what the process is. So, pardon my horrific picture here, I am not an artist, but if you can get the drift that this is, we're looking basically down from a satellite view down onto a section of California. So here we have an inaccessible river flowing out to the ocean, and then we've got some land here, and we've got some land here. Here we have the Pacific Ocean, and out here at sea is the underwater reservoir, stretching for hundreds of miles along the California coastline. So what we do is, we go to the river, and there's basically three kinds of water around the exit of the river. There's the salt water in the ocean, then there's the briny water, sort of half salt water, half fresh water, right around the mouth of the river, and then the rest of it is nice, pure, fresh river water. So what we would do is, we would go up the river far enough to get to where the actual nice, clean, fresh water is. And we would put a pump underneath the water. Then there would be a pipe taking that nice, fresh, clean river water out where it would hook up to the underwater reservoir, perhaps a few hundred yards out at sea. Let me just do that pipe a little bit better here. So it's piping the fresh river water under the ocean to the underwater reservoir out at sea. So even though I'm drawing this in black, if you were looking down from a satellite view, you wouldn't see any of it because everything is underwater. The pump is underwater and the pumping station's underwater. The pipe connecting it up to the underwater reservoir out at sea is underwater. And then if we just said, okay, we'll say, here's a city that needs some water right here. We would then take an outflow pipe and we would pump the water straight to the city. So any city in between the underwater reservoir and the mainland, running parallel to the system, could be serviced by the system. Now, let's dig down a bit deeper into some of the technical aspects of the system. As I've said, the oceanic freshwater containment and storage system would function as an invisible, under-ocean, freshwater, superhighway and reservoir system all in one. Since the underwater reservoir section of the system would need to float equidistantly between the ocean floor and the ocean surface for safety reasons, a 100-foot diameter underwater reservoir would require approximately 200 feet of ocean depth as a minimum, with no maximum depth. There is no theoretical limit on the diameter size for the underwater reservoir section of the system. The depth would have to be sufficient to provide equidistance for the underwater reservoir while allowing room for movement. All this is safely accomplished while hiding the entire system underwater. Only the buoys sitting on the ocean surface would give the oceanic freshwater containment and transport system's underwater location away. This equidistant underwater oceanic freshwater containment and transport system would stretch for hundreds of miles under the ocean surface, snaking hidden along California's coastline. Since the ocean has enough brute force behind it to break anything rigid, my next challenge was choosing which material to use for the system's construction. Again, keep in mind the phenomenal amount of potential power that the Pacific Ocean is capable of exerting. Steel or aluminum siding and walls could bend under extreme ocean events. PVC shells could fracture. And in fact, all the rigid materials I contemplated had at least one inherent flaw. Then I had an epiphany. The oceanic freshwater containment and storage system could be made out of a reinforced Kevlar-like material that bends, flexes, and moves like a blade of grass in the wind during major ocean events and storms. Reinforcing it ensures the ocean is unable to push the system flat. No amount of extreme ocean activity would be able to cause the Kevlar to break or shatter. And I'm not married to the brand Kevlar. The material merely has to have the strength, resilience, durability, and water sealing properties of reinforced Kevlar. I'm going to take a step back now and go into a more detailed explanation of what's involved here. Let's begin our journey where an inaccessible river meets the ocean, wasting fresh water into the sea 24 hours a day, 7 days a week, 365 days a year. I know I briefly went over the process earlier of the river water being pumped out to the underwater reservoir and then coming back to cities and reservoirs and storage containers along the coast. But now we're going to actually drill down and get much more detailed. So, in the area around the river's mouth, there are three kinds of water. The salt water in the ocean, the brackish water that's right around the river's mouth, and the fresh, clean river water that occurs directly upstream, perhaps 100 yards. So we travel upstream about 100 yards along this inaccessible river, beyond the brackish water. Everything's nice and clean. The fresh, clean, previously inaccessible river water is pushed through the underwater pump to an attached Kevlar system input feeder pipe. So although the entire system is made out of Kevlar, the actual feeder pipes would be Kevlar as well. As the fresh, clean, previously inaccessible river water is pushed through the pump to the attached Kevlar system input feeder pipe, that pipe would run a few hundred yards out into the Pacific Ocean where it would meet up with the system's mothership section. As the fresh, clean, previously inaccessible river water flows from the pump and into the flat Kevlar system input feeder pipe, the flat pipe would immediately expand to its full circumference, not unlike what happens when you blow up a long balloon. This would send fresh, clean water cascading into the underwater reservoir section located out at sea. Filters, sediment traps, and other measures would ensure spawning fish and fingerlings remain out of the pumping system and are as unaffected as possible by the pumping of the previously inaccessible river's water. As an aside, I believe ethically that sufficient water resources need to remain in each previously inaccessible river for aquatic wildlife and their reproductive and ecological well-being. The size and capability of the inaccessible river's underwater pump, as well as the diameter of the Kevlar system input feeder pipe attached to that pump, would only be limited by the size and flow of the inaccessible river itself. The bigger and deeper that the river is, the bigger the input feeder pipes and pumps can be. Once the water begins filling the system's underwater reservoir section, it would continue expanding the underwater reservoir until it became fully full. Once the underwater reservoir is full of fresh water, back pressure would start building up inside of the system, automatically pushing the fresh water out of any nearby Kevlar output delivery pipes all the way to the mainland. Now, as long as this pressure-driven push system is sufficient to quickly and reliably provide enough fresh, clean drinking water to those who need it, then everything's great. It's important, though, to realize that it's this push method of the system's water output delivery that allows for the use of non-rigid Kevlar for the output delivery pipes, thusly allowing most of the system to be non-rigid material based and making the entire system quite impervious to the potentially damaging power of the ocean. Once on the mainland, the fresh water could be piped on down the line or captured in storage tanks prior to moving it along to its final destination. I'll say it again, regardless of ocean events and storms, my system would move much like a blade of grass in the wind during these potentially damaging situations. The system would not snap like a tree in a windstorm like rigid materials tend to do. And again, even if it did spring a leak, there would be no environmental impact because it's just fresh river water that would leak into the ocean. The opposite of what happens when an oil pipe leaks. Remember, there are an almost unlimited number of passive push-style output delivery connection locations on the underwater reservoir section of the system. But let's assume for a minute that for some reason we get forced into a shoreline-based pull system due to extreme water requirements. When we move from a push or passive output system to a shoreline pull output system, this means the freshwater recipients use pumps on the shoreline to vacuum or pull the water out from some of the output pipes on the oceanic freshwater containment and transport system. When pulling water, however, the Kevlar freshwater output pipes we've been discussing would collapse under the suction. So either the Kevlar output pipes would need to be heavily, extremely reinforced to prevent the pipe collapsing on itself during pumping, or more likely, we would need to make the outflow pipe out of rigid material. Assuming some of the output delivery pipes may need to be made out of a rigid material for a particular city or reservoir, modifications to the reservoir section involved in such a system would be necessary. Shock absorbing and anti-puncture features would need to be built in. Also, reinforcement would be required on the inside of the walls of the underwater reservoir close to where the rigid output delivery pipes would be attached. That reinforcing would prevent the possible collapse of localized interior walls, as the water is sucked and vacuumed out of the localized sections of the underwater reservoir. Backflow inhibitors and preventers would also need to be added wherever these rigid pipes are hooked up to prevent catastrophe in the event that the rigid pipes crack or break in a storm or oceanic event. So in other words, if this is going to be made out of rigid material and then it's hooking up to the softer Kevlar material, lots and lots of reinforcement, as well as if anything on this snaps, obviously there would be sensors inside that would pick up whether or not salt water all of a sudden is in the system. And if this thing does crack and salt water goes in, we need to have backflow preventers to basically shut everything down if that happens. But again, regardless, it's much more advantageous to have multiple passive push output delivery pipes for heavy use cities or reservoirs, as opposed to one or two active pull output pipes and the risks inherent within such a system. Regardless of if the freshwater is delivered via a push or pull system, any city or reservoir running parallel to the oceanic freshwater containment and transport system would be able to receive fresh water from it. One of the first challenges that I hit along the way was, how do you get electricity to very remote areas? Inaccessible rivers often discharge their fresh water into the ocean in such extremely remote locations. Pumps installed at the bottom of the rivers need electricity to run. Where would they get that electricity from? Remember, the reason these rivers aren't already being used to provide fresh water to Californians is due to their remoteness and inaccessibility. The answer to my question came in the form of an announcement from Tesla that they were now producing house batteries that for the first time would allow folks to have nighttime electricity in their homes from solar panels that only normally provide electricity during the day when the sun's shining. So the underwater pump in the river would receive power from a solar panel array and Tesla batteries. The previously inaccessible rivers pump electricity problem was solved. With electricity available from the solar panels and the Tesla batteries, we can pump fresh water from the formerly inaccessible rivers and out to the gigantic underwater reservoir out at sea. The amount of water that the underwater reservoir section can receive is only limited by the number of previously inaccessible rivers we hook up. If the oceanic freshwater containment and transport system began off the coast of San Diego and then snaked north to where hundreds of inaccessible rivers are located, every coastal city and county along the way could be serviced by it. But it would also be capable of much more than just that. As I said before, it would also be capable of refilling the empty or nearly empty California reservoirs inland. Let's take a look at a typical drying or dried out freshwater reservoir inland. First of all, you see, reservoirs always have a path to the sea built into them for when the excess or overflow water needs to be removed from the reservoir. And those paths to the sea are called riverbeds, which are mostly dry or drying out at the moment. And by using the dry riverbeds themselves to run the reservoir replenishment pipes all the way back to the reservoir at the end of the line, most of the issues with stakeholders disappear. Dry riverbed water transport has little or no landowner involvement and allows much of the state, county, and municipal level involvement to be streamlined. Each dry or drying riverbed is literally a road to a reservoir. Pipelines would run either along the surface or subsurface of the dry riverbed all the way to the reservoir at the end of the line, connecting the coastline with the inland reservoir at the end of the dry riverbed. My oceanic freshwater containment and transport system would bring the freshwater from the underwater reservoir out at sea and deliver it to where the dry riverbed meets the ocean. Reservoir replenishment pipes could be filled either directly from the oceanic freshwater containment and transport system offshore or from coastline water storage tanks filled by that same system. As long as the dry reservoir's riverbed eventually exits to the Pacific Ocean, parallel to the oceanic freshwater containment and transport system, then fresh water can be pumped into pipes that follow the dry riverbed all the way back to the reservoir inland. Refilling reservoirs is no longer a problem. So, for a final recap, water is captured from previously inaccessible rivers on California's coastline. It is pumped out to the gigantic underwater reservoir section of the oceanic freshwater containment and transport system, floating equidistantly under the ocean surface out at sea. Then, the fresh water inside the system is output to any point along California's coast that parallels the system. Manufacturing and installing the freshwater containment and transport system can easily be handled by a factory ship, sliding the system into the ocean behind it as it slowly travels up California's coastline. The oceanic freshwater containment and transport system would run virtually autonomously with only a minimum of maintenance and a minimum of maintenance personnel required for the normal operation of the entire system. Now, everything I've talked about so far is regarding the benefit my invention would bring to the people of California in terms of perpetual, fresh, clean, unlimited drinking water. However, there would be a wonderful byproduct of this system that I haven't mentioned yet. Remember, the system I'm proposing would be at least 100 feet in diameter and hundreds of miles long, with the Pacific Ocean constantly bashing and pushing and pulling against it. My friend Pat pointed out that the amount of electrical potential of the system would be unprecedented. So I set to work immediately designing a tidal energy component to the system. I figured out that every cable anchoring the oceanic freshwater containment and transport system to the ocean floor could be outfitted with piston cylinder type electricity generating devices, or any other tidal technology option that's efficient and pragmatic. The same could be done with the cables connecting the system to the huge buoys on the surface of the ocean. From what I've been able to determine so far, there may be enough potential energy or electricity in the system to power a significant portion of the state of California's electrical grid. Remember, the force of an ocean pushing and pulling against something as large as the oceanic freshwater containment and transport system would be very powerful. Therefore, the amount of energy it would create would be incredible. Combine that with the fact that there would be literally millions and millions of cable placement locations along the oceanic freshwater containment and storage system, containment and transport system, which would be hundreds of miles long. All of a sudden, by default, you have the world's largest tidal power project of all time, and it's literally a byproduct of delivering fresh water to those in California who need it most. In fact, instead of using cables at all, I would suggest that multiple piston cylinder electrical generating units could easily be daisy-chained together to form the very cables themselves. Another benefit of daisy-chained tidal power units instead of cables would be the give naturally built into them. Unlike a normal steel cable which is taut, these daisy-chained tidal power links would each allow for give, as the pistons are moving back and forth inside the cylinders. The energy would also be scalable. If California needs more electricity somewhere down the line, then extra tidal power cables could be attached very easily. Even an entire secondary oceanic freshwater containment and transport system could be installed to run in parallel with the first one. Not only that, but if needed, it could stretch along the entirety of the California coastline. Add more cables with green tidal energy technology incorporated, get more electricity. The loose fabric nature of the Kevlar would help it catch the current and increase the force of the ocean currents against the underwater reservoir section, thereby increasing the amount of potential energy in the system as a whole. Also, once the tidal power electrical generation component of the system is fully implemented and integrated, the solar panels would no longer be needed any longer at the river sites to run the underwater pumps. Only the Tesla batteries would still be retained for electrical backup purposes, as the oceanic freshwater containment and transport system itself would be producing so much free electricity. Of course, the intended priority of the system is the transport and storage of fresh, clean, abundant, previously inaccessible river water, not electricity per se. But we're happy to have the best of both worlds. If one of the pipes ever springs a leak, remember, the ocean would just receive a burst of fresh river water, the exact opposite of what occurs when an oil or gas pipe springs a leak. Although the system would be made primarily out of Kevlar, obviously cables, tidal power equipment, anchors, fittings, couplings, bands, attachment areas, cables, cable ties, valves, sensors, inner and outer reinforcing membranes, and there's a lot of different things that would not be made of Kevlar. I mean, obviously, they would have to be made out of rigid materials such as carbon composite or brass or titanium or basically whatever engineer-approved materials are going to work for the particular situation. The Kevlar is designed for the walls. The purpose of the Kevlar is for the walls or for the Kevlar type material. Now, I'm leaving those kinds of fine details to the Army Corps of Engineers, since it's very likely they would be the people actually building this system. The reason why I think the Army Corps of Engineers are the best group of people for the job is You know, they learned from Hurricane Katrina, and they came and they redid the levees after Hurricane Katrina. They're used to, you know, gigantic pyramids of Egypt-sized jobs, and really that's what we're talking about here. We're talking about a gigantic-sized job. So also, some things that would have to be incorporated into the underwater reservoir would need air release valves in the top sections of it. It would also need sediment release traps in the bottom of it, because as the water is coming into the underwater reservoir, you're naturally going to get air and sediment coming into the system. And so, yeah, you would need release valves, obviously, for those, and other servicing related different equipment, and also monitoring components would also need to be installed. Again, I'm leaving all those details to the Army Corps of Engineers. Manufacturing and installing the oceanic freshwater containment and transport system could easily be handled by 1 or 2 factory ships, essentially sliding the sections of the freshwater system, of the underwater reservoir into the ocean behind the factory ship as it slowly travels up the California coastline. Now, if illegal drift netting factory ships are found by the US Navy in American waters, those ships could easily be appropriated and retooled, basically to lessen the cost of manufacturing and installing the system. And at the same time, we would be getting rid of some bad miles-long drift net fishing ships. But regardless, so right now I want to take a look at some of the potential foreseeable concerns with such a system as I'm suggesting, which may or may not be obvious. The first concern was, could there be a harmful increase in ocean salt percentage as the returning water is diverted? Because keep in mind, we're talking about diverting billions of gallons of water that would normally end up in the ocean. So is the ocean going to become saltier? Well, environmentally speaking, removing ocean water in such a level, you'd think it might be a problem, but luckily for us and unluckily for the planet, the Arctic and Antarctic ice caps are melting at an incredible rate and adding an immense amount of fresh water to the oceans of the world in the process. So I do not think salt percentage increase is an issue here. The next concern was, what if terrorists decide to attack it? In contemplating this, I realized the terrorists have access to much less difficult soft targets if they chose to attack California. It would be much easier for a terrorist to poison a reservoir itself than it would be to try to attack something 50 feet underwater with a positive pressure inside. It's much easier just to actually go to the inland reservoir and poison the water there. So yes, when you're talking about something 50 feet down, positive pressure inside, yeah, it's not going to be easy. Monitoring equipment could easily be installed inside the buoys, as well as on the outer walls of the oceanic freshwater containment and transport system itself. So in that respect, the system is not much more of a risk than any other target. So then the next question I had was, would the underwater reservoir section of the freshwater containment and transport system block the light from the ocean floor, harming the ocean plant life on the ocean bottom? Keep in mind, the oceanic freshwater containment and transport system would be shaped kind of like a snake. And as the sun crosses the sky, the shadow it would cast would move across the ocean floor. Although I cannot say if this would or would not harm undersea life, please keep in mind we're talking about an average minimum depth of 50 meters. And that kind of depth, there's not a lot of light to begin with. So at this point, it's a risk we have to take. And a minimal risk, in my opinion, considering the reward a system like this would bring Californians. If the oceanic freshwater containment and transport system were to suffer a catastrophic accident and release a massive amount of fresh water into the ocean, what effect would that have? So I had to give that some thought. Due to the sheer size of the Pacific Ocean, any massive freshwater infusion would be dissipated within hours. It would be harmlessly mixed together with the ocean's salt water. This is actually the exact opposite, as I've said before, of an oil spill. So what's the next concern that I managed to figure out? Will this oceanic freshwater containment and transport system disrupt the migratory patterns of sea life? That was the next question I had, trying to figure out, is this thing going to harm anything? The system certainly would not prevent sea life from migrating around it. Any sea life intelligent enough to migrate in the first place should be able to swim around the underwater reservoir and should also be smart enough to avoid undersea hazards. On the plus side, herring stocks would increase dramatically, since herring would attach their eggs to the outer walls of the underwater reservoir. In fact, lower food chain fish should see their populations increase, as the system would provide additional hiding places from predators. Should the government decide to do so, a lump sum could be paid to the Kevlar patent holder for license to manufacture unlimited, genuine Kevlar for this product, minimizing the cost of the Kevlar. Alternatively, some form of governmental eminent domain could also work. And finally, if a deal can't be struck with the Kevlar brand per se, there are many competing industrial Kevlar-like fabrics that offer similar properties to Kevlar. According to my estimates, the oceanic freshwater containment and transport system would provide more water than needed by California residents, even businesses, and also farming and fossil fuel extraction. Now, although I will be patenting my invention, unlike many traditional patent holders, it is my intention to give the water storage and water transportation components of the oceanic freshwater containment and transport system to the people of California, since I consider access to fresh water to be a human right for every Californian. It is also my intention to give half of the electricity component to the government of California to help them in their quest to power their state from green energy as the primary focus of electrical power. So, where do I go from here? The next steps I'll be taking will include contacting both California Governor Jerry Brown as well as the Lieutenant Governor of California, Gavin Newsom, to discuss the feasibility of implementing the system. Hopefully, I can get enough support to take this to the next level. So, in signing off, my invention would allow the capture of fresh water from otherwise inaccessible rivers, transport it to the oceanic freshwater containment and transport system under the ocean surface, out at sea, and deliver it to any coastline location between the oceanic freshwater containment and transport system and the mainland of California. I believe I have found the ideal solution that is also the most cost-effective solution, while also being a long-term grassroots fix for California's freshwater availability issues. We're constructing a website with the system's acronym.com, so that's it's the Oceanic Freshwater Containment and Transport System, so the website that we're going to be building is ofwcats.com or ofwcats.com if you like, but it's going to take a few weeks to get it up and running. Thank you very, very much for your time, and God bless California.